again, because we have something that's decreasing in magnitude, making it an alternating series, so the limit would have to, of a sub n have to go to 0. It's decreasing in magnitude. And as it turns out, that the error of your approximation will be bounded by the first truncated term of the partial sums. So what I would need to do is pull out the relevant pieces here. All right. Just in order to do the calculations. But really, I mean, the top is really just to give me a sense of the sign. And you just need to know in what way it's bouncing back and forth, positive to negative or negative to positive. So in the case of this one, it's starting at 1, even power, it's starting with a positive. 1 over 1 to the 4th. Then, that looks like a 14, kind of. It looks too much like a 14 that I'm going to change it. All right, and then negative 1 over 2 to the 4th, 1 over 3 to the 4th, negative 1 over 4 to the 4th. And the idea is that you keep going until your truncated value has a measure less than 1 over 1,000. All right, so you're going to need to do some calculation in order to get a sense of that. So I would look at 4 to the 4th, for example.
You said you can start from the positive because the n is plus 1, n plus 1?
N plus 1, but specifically because we're plugging in a 1 for n to start. So that gives us an even power.
Oh, I got you. Because on the one above it, it's minus 1. That wouldn't make a difference. It's still going to start positive because...
Right, because you're starting with an even exponent.
Okay.
All right, so 1 over 256 is what 1 over 4 to the 4th would be. 1 over 256 is not smaller than 1 over 1,000, so keep going. So 1 over 5 to the 4th, that's 1 over 625. That one I just happen to know. That's not smaller. I think this is 1 over 1296. I'll double check that one. Yeah. 1 over 1296 is smaller than 1 over 1,000, so that would be our first truncated value. Now, at this point, doing the calculations by hand is not a big deal to get our approximation. But you could also just actually run a summation. Alpha, window, option 2. Plug in whatever I like I mentioned that. I mean, they use n, but it doesn't really matter to me. And it doesn't matter to anyone because the calculator is going to understand it. I'm going from the first term to the 5th term. And then I would just type in my original a sub n, quantity. Only part of it, because it's alternating, only part of it's actually a sub n. Numerator or denominator. Bring this up a smidge. Negative 1. Although in the time it takes to type it in, you may have already figured out the actual sum. But
how many terms did we have to do? Like 4 or 5?
We had to do 5. Because it was the 6th term that gave us a value less than 1 in 1,000. So you get that. Really? I screwed it up?
Yeah, what if it's 5 versus less by 5?
Huh. Thought I knew math. I'm getting false. Okay, so 1 divided by 5 to the 4th in decimal form. But you typed in that and you got something different? No, I was thinking, well, it sounds like 1/200th of the correct answer. So I'm like wondering how that might have happened. Yeah, I don't even know. We can look at that in a few minutes. Maybe. To get a sense of it, yeah. Yeah. I mean, in this case, because your numerator is equal to 1, it's pretty easy to compare if you actually have the correct value. But this is 1/625. You're dividing 1 by a smaller number, so this would naturally make this a bigger fraction. So it's kind of like that whole parent EBM thing that we were talking about. To start with, based on the operation, because you have a -1 raised to the n plus 1 power. If I plug in a 1, that makes this a 2. Raising a negative to an even power makes it positive.
Quick question. How do you turn your answer to a fraction of the calculator?
Math, enter. Math, enter. And then, if it's math frackable, it'll convert over. I think I lost my answer though, so let's go back into history.
So then you stop at whatever is right before the sum you need less than. So like since you need less than 1/1000, you stop at
the one right before that.
Okay.
All right.
Use a laptop, that program that you gave us.
A laptop?
Not a laptop, but you gave us the program that gave us the approximation. The text on the scene.
Oh, the Taylor polynomials?
Right.
Oh, we're going to get to that in a little bit, but yeah, you can't use that on a test. Yeah, that'd be nice.
Forever.
So we need 5 terms, because that's what it was asking. How many terms needed to approximate the sum? So we would need 5 terms in order to get something that's to within 1/1000th of the correct overall sum. And if you're willing to sacrifice even more accuracy, maybe you don't have to go as far out in the truncated terms. Before you truncate a term. Benefit of an approach like this allows for cases where it's not strictly n-based. So you have a summation that maybe involves a variable x, like the summation is actually a function of x. So to know that you would only have to go out a certain number of terms in order to have reasonable accuracy, that's going to be a good thing, right? Because then it means you don't have to work with potentially infinitely many terms of a sequence when trying to find a derivative or an antiderivative.